Good morning, everyone. We have a fair amount to do today. So we need to talk about, today we're talking about conductors, which are in some ways more interesting than insulators. And here's basically our agenda. We want to talk a little bit more about the difference between conductors and insulators and the conventions we use in diagrams to make clear what's going on. Charge, motion, and conductors, how conductors polarize. We talked about polarization of insulators last time. Kind of how metals work, and about mechanisms for charging conductors. So we have a lot to cover today. Let's start with review. So we found that we could charge invisible tapes by just pulling them off some other surface that we don't know quite whether electrons got transferred or ions got transferred, but the net effect is the tape is charged. So if we hold a positively charged tape near our hand, which of these diagrams best shows the polarization of a molecule in your hand by the tape? Okay, so here's what you said, and that's excellent. That's great. So indeed, we have the so one is indeed the correct answer. Let me get rid of this little window here. 5 means, okay, so 5 means no charge separation. Since we're not showing separated charges, that nothing, there's no change in a neutral molecule. So, and that raises an interesting point about these diagrams. We know that there's lots and lots of charges inside objects. Matter is made of charged particles. If we drew them all, though, for a neutral object, we draw equal numbers of pluses and minuses, but then it would just become such a cluttered diagram that we'd actually have trouble interpreting it. So by convention, if something's neutral, we just don't draw any charges. If it's not, if there's no charge separation, then we don't, and it's not polarized, so not polarized. So in fact, one is indeed the correct answer, and we can think of it as the charged tape producing an electric field here inside your hands that affects the molecules inside your hands and polarizes them in that direction. So excellent. As a result, now that these molecules are polarized, what happens? What's the effect? What's the resulted effect? So what's the direction of the force on the tape due to the polarized molecules in your hand? And again, that's the right answer. Three is the correct answer. So that the tape is attracted to your hand because of the electric field made by these polarized molecules. So now that these molecules are polarized, and so what we have here is negative there and positive there. These dipoles in your hand make an electric field at the location of the tape, that points toward the hand because the negative end of the dipole is a little bit closer than the positive end. So we have E dipoles, and then that results in a force on the tape to the right. So it's attracted to your hand. And we worked through last time what would happen if the tape was negative, and we decided the molecules would polarize the other way, and so the field would be the other direction, and so the tape would still be attracted to your hand. So we found that neutral objects were all, and charged objects always attracted each other due to this polarization. Now, a little piece of vocabulary here. It is possible for something to be polarized and charged. Polarized and charged are different. So here's a piece of insulator. Maybe it's a blob of plastic or something. And we have a little bit of excess charge on the surface. Maybe due to rubbing it with wool or something like that. And we note that the charge, because insulators don't have mobile charges, the charge stays in this little patch, doesn't move. So this object is charged because its net charge is not zero, but it's also polarized because this excess charge affects the molecules inside this insulator, so they polarize. So an object can be both charged and polarized. And for some reason, not clear why, this particular object even has a positive charge embedded. Maybe someone shot a proton into it with an accelerator. And it's stuck there. It can't move. Okay, there's no way for it to move. So again, it's affecting these molecules too. So one of our diagrammatic conventions is that this is anytime we're talking about charge on the surface, we draw it just outside the envelope of our object. Okay, so this is supposed to indicate that it's sitting on the surface. So this would be a charge in the diagram inside surface, and this is a charge on the surface. And that way we can distinguish what we mean by a diagram. Okay. So one of the things we said about insulators was that insulators have no mobile charges. Which means that inside the electrons are bound to the molecules. They can't move. They can move a little, they can shift a little bit, but they can't move very far. Whereas in conductors, so bound electrons can't move very far. So less than 10 to the minus 10 meters. Conductors, there are mobile charges that can move really long distances. So in recitation last time, we briefly talked about something like salt water. So an example would be salt solution, where we have we've got water, but we have sodium ions and chloride ions floating around in the water. And these things can move long distances. So this sodium ion could actually move many centimeters to the other side of this beaker, or if it's in the ocean, it could move miles. Okay, so it can move long distances. I suppose I should write that so it's actually legible. And that's very different from being bound and only being able to shift just a little bit. And so if we applied an electric field here, let's suppose that there's something outside here that we don't know that creates an electric field. And we don't know what the sources are. There could be positive charge on the right, there could be negative charge on the left, it doesn't matter. But if there's some electric field due to outside sources here, then these charges can move. And so what we'd get is, we'd get sodium ions sort of piling up here. And we get chloride ions kind of piling up on that side. And then there'd still be other ions in the middle. And we'll talk about how far this process goes because it's an interesting issue. Now, since these things can move long distances, and that presumably their motion is proportional to the applied field. If we apply a small field, they're probably going to move slower than if we apply a large field. We actually have a relationship that we can write down mathematically. So the speed of a charged object in a substance like a sodium ion in salt water is called its drift speed. Why is it called its drift speed? Because what happens is even without any electric field, all these things are moving around a lot, right? They're finding collisions with water molecules, maybe collisions with other ions. So there's a lot of random motion, even when nothing's disturbing this. When an electric field is applied, that random motion doesn't stop, but all of the charges begin to drift in the direction that they're experiencing a force. So that's sort of superimposed on top of it. It's actually like wind and air. So air molecules are moving around at reasonably high speeds. But if there's a wind, then they don't stop this random high-speed motion, but they all kind of drift in the direction of the wind. So that's the metaphor here. So drift speed is proportional to the applied electric field. And drift speed is going to be an average thing. They're not all moving at the same time. So we write it as with a single bar across here. This is not a vector. Right now we're writing a scalar equation. So this means average. That's a notation for average. So the drift speed depends on the magnitude of the net field at the location of a charged object. And the proportionality constant is called the mobility. And so if something's really big, like chloride ions are really big, and they probably have lots of water molecules surrounding them. So they actually sort of feel more drag. So their mobility would probably be actually less than the mobility of sodium ions, which are smaller. So different circumstances create different mobilities. Now let's see what the units of this have to be. So this is going to be meters per second. Net electric field has units of newtons per coulomb. So this actually has to have units of meters per second per newton per coulomb. So for example, the mobility of a chloride ion in salt water is on the order of 8 times 10 to the negative 8 meters per second per newton per coulomb. So if we have a net electric field of 200 newtons per coulomb inside a beaker of salt water, and of course, we're talking about the net field at the location of a charge. So what's affected by this net field? Well, some charge that's at that observation location. Then the average drift speed of a chloride ion would just be the mobility, 8 times 10 to the negative 8 meters per second per newton per coulomb, times the net electric field at the location of the chloride ion, so 200 newtons per coulomb. And so we'd get something like 16 times 10 to the negative 6th meters per second, or 1.6 times 10 to the minus 5th meters per second. So not real fast. But there's a lot of chloride ions in there. So you can get a lot of charge motion even if any individual thing is moving slowly. Okay, so let's consider what's going to happen if we apply electric field to a conductor, let's say salt water. So polarization conductor. So we'll start out with our salt water, and here I'm going to just draw it schematically. We have some plus charges and some minuses. And since I'm not drawing envelopes around them, they're not bound to anything, they're free to move. And now we're going to apply an electric field to the right, let's say. So here's our electric field. We'll apply it to the right. And again, applied just means by external things. And we'll see in the next chapter that it actually is possible by arranging charges to make an electric field that actually is pretty uniform within a region. So let's say we've actually got a uniform electric field here throughout this. So what's going to happen? Well, positive charges are going to move in the direction of the electric field, and negative charges are going to move in the opposite direction of the electric field. And so here's our applied electric field, which is still there. And we're going to start getting positive charges building up here and negative charges building up here. But we still have some pluses and minuses here, which I normally wouldn't draw, but for this argument, it makes sense. Now, how far does this go? So does every charge so could we possibly end up with a situation with all the negative charges here and all the positive charges here and nothing in the middle? And the way we reason about this is kind of interesting. It's actually it's a use of formal logic that's called proof by contradiction, and it's actually a very rigorous way of reasoning about something. So proof by contradiction works by you assume kind of the opposite of what you want to prove. And then you show by reasoning what would happen if that were true, that you reach some sort of logical contradiction. And so you have to conclude that the thing you assumed, which is the opposite of what you wanted to prove, is actually false. And so therefore the thing you wanted to prove is true. So we're going to frame this way. So at equilibrium, so what does equilibrium mean in a conductor? It means that the drift speed of charges in the conductor is zero. So there's no longer bulk charge flow in any case. The drift speed is zero. So the charges are still moving around randomly, but they're not going anywhere. Basically, it's a null hypothesis, basically, yeah. So if the drift speed is zero, then we can guess that inside this conductor, the net electric field must be zero. Because if the net electric field isn't zero, then the drift speed is not going to be zero, and you're still going to get charges separating here. So in our proof by contradiction, here's what we're going to do. So we're going to assume that the opposite of what we want to prove. We're going to assume that the electric field, the net electric field, is non-zero. I'm writing magnitude, so greater than zero at equilibrium. And then we're going to show that that's a contradiction of our definition of equilibrium. So we assume that the net electric field in there is greater than zero. So remember, we have this applied electric field. Well, if we assume this, then all ions have drift speed v drift is UE net, which is greater than zero. And since the drift speed is not equal to zero, then we're not at equilibrium. So here's our contradiction. So that means that this must be, our assumption must be false. Which must mean that the net electric field, so we conclude that the net electric field, so conclusion, at equilibrium inside a conductor, the net electric field must be 0. Well, that's kind of a problem, because here we had this conductor, salt water. So we have our salt water solution here to be concrete. And we applied an electric field to the right. And we said that this would polarize so that we had some excess negative charges here and some positive charges here. But we've still got this applied field. It hasn't gone away. So how can E net be 0 inside? Well, let's think about it like a comic strip in step by step. So here we have our applied electric field, and in a short time, a nanosecond or so, what's going to happen is all the chloride ions in the solution are going to move a little bit to the left. So all of our chloride ions are going to move that way, and all of our sodium ions, oops, I want to make those green, are all going to move a little bit that way, and some of them are going to run into the wall. So we're actually going to get a few negative ions over on this wall, and we're going to get a few positive, I'll draw them plus, positive ions on that wall. Well, now we actually have some new charges that are kind of naked. So we have something that kind of looks like positive charge on the right, in excess of positive charge on the right. And we have excess negative charge on the left. And so this is another source of field. It's still neutral in the middle here. But now these excess charges themselves make a field. And it's going to be in the other direction because we've got the negative charges on the wall here. So now we're talking about these new sources. So these negative charges make an electric field that way, and the positive charges make an electric field that way. So now we've got actually another contribution to the electric field in here. We have the electric field due to these polarized charges. And so our net field here is going to be the sum of the applied field and the field due to polarization. And so our net field here is going to be still to the right, but smaller than it was, because we're adding this vector to that vector. And so our net field is actually going to be smaller. So now we have a net field, I'll draw it down here, that's smaller. Now it's not 0, which means this thing will still keep polarizing. So in the next nanosecond, we're going to have a little more. The negative ions are still moving to the left. The positive ions are still moving to the right. So we're going to have more negative charge build up here and more positive charge build up here. So now we've got this E applied, but the electric field due to these polarizing charges is getting larger and larger. So E net is now smaller. And this goes on until we get to a situation where we have enough negative charge here and enough positive charge here that the applied field is just exactly balanced by the field due to these this charge buildup due to the polarization, and E net reaches 0. And after that, there is suddenly no force on these charged on these sodium ions and chloride ions, and so they drift to a stop. So why don't they keep moving? We know that Newton's second law says that something that has a 0 net force on it should keep moving. Well, this is an environment where there's something like friction, a lot of it. They keep running into water molecules, other hydrated ions, and losing energy. And so, in fact, the drift speed comes to a stop. So we proved here, this is not an assertion, we actually proved that at equilibrium, E net in a conductor and now we have a mechanism. We see how that happens, because the conductor polarizes just until the field made by the polarization is equal and opposite to the applied field, and so then that field becomes 0. Okay, so we know salt water is a conductor, but we also know metals are conductors. So how does this work in metals? Our model of metals, we had this ball and spring model of metals where metal atoms are so we had a ball and spring model where metal atoms connected by chemical bonds to other atoms, and these are covalent bonds. So where are the mobile charges? Well, what actually happens in metals is pretty interesting. It turns out that a pretty good model of what happens in metals is that because there's so many metal nuclei, it behaves in a certain sense like kind of a giant molecule. So each atom gives up one electron. And so we have this cloud of electrons, and it's actually called, described as the mobile electron sea. So we have a sea of mobile electrons. So in a metal, what we end up with is now, since we have a bunch of ions that are still bound together, but what happens, so we've got now each each of these nuclei is slightly positive because it's given up an electron. And we have this kind of sea of mobile electrons. They're mobile electrons that can travel throughout the piece of metal. So if the piece of metal is a centimeter long, they could travel from one end to the other. If the piece of metal is a meter long, they could potentially travel a meter. If it's a power line stretching many kilometers, then they, any mobile electron could travel that far. So it's a mobile electron sea. And so that means that even though the nuclei can't actually move, they're still bound. The mobile electrons can. So what happens? So here's so schematically, we'll draw our piece of metal as having lots of these positive atomic cores here, we're going to call them. So these are positive, let me call this some other color, green. Positive cores, they're atoms that have lost one electron, basically. And then we have here our sea of many mobile electrons that can travel throughout the whole thing. So this is the mobile electron sea. So what happens here if we apply an electric field? Well, let's say we apply an electric field that points that way. How does this metal polarize? What's going to happen here is the entire mobile electron sea can actually shift to the left a little bit. Positive charges can't really move, but the mobile electron sea can shift to the left. So what happens is all these electrons are going to basically shift to the left, and we're going to actually have an area here where there aren't any mobile electrons. So if we draw it schematically, what we're going to end up drawing is we're going to draw a bunch of electrons, and we're going to draw it just outside the metal envelope to show that it's sitting on the surface of the metal. So excess electrons on surface. And over here we have some positive atomic cores that are exposed. Now they're kind of sticking out of the surface at this point because the electrons. So we're gonna draw the positive atomic cores, and I better draw the same number of excess ones I do over there. So excess electrons on surface, exposed positive atomic cores. So these can actually move. Okay, so what does this really look like? We do have a VPython program for this. Okay, so what this is the result of a computer calculation done actually in VPython, but not here in real time. Because it takes a long time to actually do the calculation. So what's done is to sort of divide this is a metal block, a neutral metal block, and it's being polarized by this external positive red charge here. And this is a calculation of what the charge distribution on this block is going to look like. Blue means negative, so these on this end, the left end, we've got excess electrons piling up here on the left end. Red means positive, so on the right end we've got a lot of exposed positive atomic cores, and where it's white, it's neutral, so there is no excess charge. And we can see it's not symmetric, right? This is what it would be at equilibrium. So we get this charge separation. Why isn't it just equal amounts of positive and negative charge? Well, it's because the thing that's polarizing it is not creating a uniform field. It's a point charge, so the field falls off like 1 over r squared. So we can see here, if we drag here, we can see the net electric field at some observation location. So around this thing, if we're near the source charge, it's very big. Near the block, and now what it's going to show us is the electric field inside this block, but it's going to draw it on the surface so we can see it. So now if I drag across here, we see that everywhere the net electric field, there's a zero length arrow here. It's just that little wibbly thing here. So we've actually got an electric field that somehow magically comes out to 0 everywhere inside this block. Well, let's see how that works. Instead of the net field, let's show the electric field due to the external sources, that's the point charge, and the electric field due to the charges on the surface of the block. So the magenta field is the electric field due to this point charge. And we can see that the charges on the surface of the block are contributing something even outside. If I move off the axis, it's a little easier to see that green arrow. So that pulls. Okay, and as we get close to the block, that gets bigger and bigger. And then when we're inside the block, the charge distribution on the block is such that absolutely everywhere in the block, the net electric field manages to be 0, even though the electric field of this applied field is not uniform. So it's stronger at the left end and weaker at the right end. But we see that this polarization manages almost magically to create a field that's exactly equal and opposite to the field to the applied field. Yeah, it's pretty cool. And the reason it works mathematically turns out to be that the electric field falls off exactly like 1 over r squared. This actually wouldn't work if it didn't. So that's an interesting fact. Okay. So let's see if it's possible to apply this. What can we do? How can we think about this? So we have a region of space in which there's an applied electric field due to external charges that's pointing upward. And we place a neutral copper block in this region. So how would we draw, which diagram best shows us the distribution of charge in or on the copper block? Okay, so we've got these 5 possible charge distributions on the copper block. Well, the majority's right, but it's not unanimous. So let's see. Let's make sure we're on the same page here. So 1 is indeed the correct answer. So let's see why. So it really helps to draw these things. So we're gonna draw. So here's our neutral block. We're going to draw the applied electric field there. And now we have to think about the mobile charges in the block. We have these mobile electrons C because it's copper. And so each electron here, an electron at this location here, is going to feel a force opposite to the field. So all the electrons are actually going to shift down. So what we're going to do is we're going to get a pile up of electrons here. And even though the positive cores didn't move, what we've got now, we've exposed some of them. So we have these exposed positive cores here. So that's correct. Okay, what would happen if we started out with slightly different situation? So suppose we start with an iron block that actually is already negatively charged. So it already has an excess of negative charge. What's going to be the situation? So what do we have? 5 again. So which of these diagrams is going to represent what happens with? We have an electric field down this time. Okay, minus y it says. Okay, 2 is the most popular answer, but 3 is also popular. And 3 is actually a significant, the way these diagrams are going, 3 is a much better answer than 2, as we'll see here. So why is that the case? Well, in this diagram, the number of pluses equal the number of minuses, so the net charge is 0. But we know that the iron block was charged negative. So even though the direction is correct, we'd certainly have, if we have an electric field down, then an electron, a mobile electron, would feel a force going up. So we certainly would get electrons on the top surface, but we have a net charge of 0 in this diagram. So a better answer is this one, where Q net is not 0, where we have more negative charge on the top and less on the bottom. The polarizability, a polarizability of a metal is, remember we had a dipole moment is alpha E for a molecule or something. The polarizability of a metal, a conductor, is essentially infinite, actually. So polarizability isn't the word you want to use. But what's going to happen here is that we started out presumably with kind of an equal distribution of negative charge around. Although, as you saw in that computer calculation there, you actually end up with a lot more charge on edges. And it just works out that way. It's a little counterintuitive, but it does work out that way. And so, but then when we apply the field, what would happen is that here's our field. We get negative charge shifting down here. And now we've got a lot more negative and less negative, more negative on the bottom, less negative on the top. So the contribution to the net field of these charges would be that, I mean, sorry, I've got it backwards, don't I? Yep. So a lot more negative on the top than on the bottom. So here's our E applied, and the negative charge on the top makes a field, a big field. Whoa. Negative charge on the top would make a big field. The negative charge on the bottom would make, and so the sum of those two things would be equal and opposite to the applied field. So yes, so the field within the block comes out to 0 because of that. Electrons always move opposite to the net field no matter what. So so remember that this vector equation F equals QE describes forces on particles. So if Q is negative, that says that the direction of the force is actually going to be opposite to the direction of the field. So an electron always, the force on an electron, if we have an electron here, and we've got a field down, then the force on the electron is actually always going to be opposite direction of the field. So that's really an important thing to sort of remember. Now there's another thing about conductors that seems plausible, but we can't actually prove it yet. And that's for a conductor, excess charge always ends up on the surface. Is this something you have to memorize? Yes, there are two things you have to memorize. You have to memorize that equation, which will not be on equation sheets, and that's fundamental. And you also have to memorize the equation for the electric field of a point charge. So that's one thing to memorize. And the other is now it's sort of so actually it turns out that when we get to chapter 21, we'll be able to prove it. We can prove it later. But it's pretty plausible. I mean, because if you had a metal block with lots and lots of, say, excess electrons in here, they would repel each other. So of course they'd want to get as far away as possible, so they'd move out to the surface. So it's a completely plausible assertion, but we actually just don't have the formal tools to prove it quite yet. Okay, I want to talk a little bit about how conductors can get charged, so and discharged. So charging and discharging, meaning removing excess charge, conductors. Okay. So let's consider a question here. So we have two identical metal blocks here. But the only difference is that initially block A is neutral. I mean, block A has a charge of +6 nanocoulombs, meaning that it has a deficiency of electrons. And block B is neutral. And so we bring them together and let them touch. and then we move them apart. What do you think the final charge of block B is going to be here? So some uncertainty, the most popular answer is 2. So most popular answer is +3 nanocoulombs. And that's a pretty plausible answer. So another popular answer is 0. And I'm not sure why -3 is a popular answer. So maybe we'll have to talk about that. But so let's talk about this for a minute. So here we've got a deficiency of electrons in block A. A has fewer electrons than it has positive cores, and block B is neutral. We have exactly the same number of electrons. When we put these blocks together, the minute they touch, what is the electric field inside block B going to be? We have all this positive charge here in block A, and it's certainly going to make an electric field inside block B that points away. And what's that going to do to electrons in block B? Well, if we have an electron in block B, it's certainly going to feel a force toward A. So electrons in B are going to move toward A. Now, when they get there, if these blocks are touching, is there anything to stop them? There's actually nothing to stop them from just moving on to block A. And so electrons are going to start moving on to block A, meaning that block A is going to get less positive. And now we've lost some electrons from block B, so B starts to get slightly positive. And we don't have to wait very long. One of the things about these processes, whether it's charging or polarization, is they're really fast. So these processes occur in nanoseconds at most. So we don't have to wait very long before enough electrons have moved into block A that now there's equal amounts of charge on each block, and the electric field in here ends up going to 0. So when we move them apart, we're actually going to have some positive charge on block A and some positive charge on block B. Some of the electrons moved. And so, in fact, given that the blocks are identical, they will now each have half the charge of the original. Now, if they'd been insulators, the story might have been different, because since there aren't any mobile charges, if we touch the insulators together, except for charge that's right at the surface that might decide that it's happier being bonded to block B, there's the charge on block A really can't move. And so we could bring them together and take them apart, and the charge of the blocks wouldn't have changed. A would still be positive and B would still be neutral. But the fact that they're conductors, conductors meant that. So this is called charging by contact. And that actually leads to another phenomenon, which is which could explain discharging also. So suppose that we have a metal ball. So here's a metal ball that has excess electrons, so it's negative. And what we've got over here is a human. So here's our human. What happens if, and the human is neutral. What happens if the human touches the ball? So are we conductors or insulators? It could be hilarious. But what actually can happen is, although we're not made of metal, we actually do have on our skins a film of salt water, sweat. So we've actually got a conducting film on us here. And so we've got plus and minus and plus and minus. And so, in fact, because we have a conducting film, electrons can flow off the metal and onto our hand. So here's, we'll move the human over so they can actually touch the ball. At which point we can get electrons flowing up here, and what would they do? Well, they could react with a sodium ion. So we get sodium metal. That would be exciting. Sodium hydroxide, probably not a lot. We could also get sodium ions flowing off our hand onto the ball. And so now the question is, which has the biggest surface area, the most room for charge to spread out? And if this ball isn't gigantic, what's actually going to happen is that the charges, most of the charge on the ball will actually move onto the bigger surface so it can spread out more. And so what we're going to end up with is a human that has now a lot of negative charge spread out over a big surface, and a ball that's close to neutral. So we've neutralized by touching. This is sometimes called grounding. Because one way to neutralize things and make sure they're neutral is actually to have a conducting object run from a charged object down into the earth. So the earth has a big surface area, and it's got lots of ions and water in the soil, so it's not a bad conductor. And so if we make a wire, say a metal wire, go down here into the earth, this thing is grounded and charge will flow off the object, and down into the earth where it actually. So is that why when you're replacing computer components, they suggest you touch something made of metal before handling the components? It is essentially, yes, that's exactly right. It's to ground yourself, because if you come in with a big charge that you might have gotten by shuffling across the carpet and having a static charge build up on you, a spark can actually go from you to the components. You can make a current in there, and that will fry them, and then they won't work, and that's undesirable. So that if you touch something that's large enough and made of metal, any small charge you might have on your surface can spread out into the metal. So we call it neutralizing. Okay. Yes, dad jokes about grounding. And so presumably there's now, a while back, Mitch asked about how we neutralize, why a charged tape got neutralized when we ran our fingers across it. And the answer presumably is that we are discharging it because ions from our skin can flow onto the tape. And so we actually, we add oppositely charged ions and the tape gets discharged. There's another kind of charging that we'll talk about very quickly. This is called charging by induction. And the basic idea is this, that we use polarization to make a charge. So initially, these frames go 1 time 2 times 3 times 4. So if we take some neutral blocks and touch them together, and then we bring a positive charge near block A, but we don't touch it, then leaving the positive charge there, we carefully move block A away from block B with touching it with an insulating handle. And now we take the positive charge away. It can end up that block A has a net negative charge, and block B has a net positive charge. Okay, how does that happen? It's surface area that's important in grounding, because the excess charge wants to spread out. The excess charge is going to be on the surface. And so excess charge spreads out over a surface. So basically what we have here is that when we've got these blocks touching, so this is time 2, and we've got a positive charge here, we polarize these things so that we get excess positive charge here and we get excess mobile electrons here. So, and now if we carefully leave this positive charge here, but we separate the blocks, what was one big polarized block now becomes 2 charged blocks. So then when we take away the positive charge, so this is time 3, this is time 4, we take them away, we've actually got 2 blocks that are negatively charged and positively charged, and if they're close together, they're probably going to polarize each other that way. This is called charging by induction. Okay, so I think we got through everything we were supposed to get through. It's a lot, and it's a lot about properties of matter. But going forward, this is actually going to be important, because how almost all everyday phenomena involving electricity have to do with how matter reacts to electric fields. So we need to know something about the properties of matter in order to analyze these phenomena correctly. Okay, so the net charge of A actually ended up being negative. All right, so for attendance, could you please type in chat either what you think the most important idea to take away here is, or the most interesting idea that's come up in today's discussion. And we'll practice with this stuff in recitation this afternoon. Drawing diagrams is really, really important. And not just the idea that E net is 0, but in a conductor at equilibrium, but that why.